Good afternoon, this is Schweitzer. We're going to go through a little bit on the quadratic formula and kind of look at how we use it in our class and then give you just a little familiarity with it. Obviously, if you've gone through some math classes, you've seen this. So anytime you have a quadratic formula is where we're using to solve a multivariable equation. So it's going to look like this, where we have some number, let's say, yeah, so some number, and then it's going to be another potential number, and then we have plus some value x, y. In fact, let's just change this out. Um, they're going to call this number C, and then they're going to call this number B, and then there's going to be a variable, not for us, that variable is going to be time, and then another variable here, which is going to be A, and then our time is squared. So if you look at this quadratic formula, it looks very similar to our S formula or our distance formula, which is going to be xt equals xi plus 1 plus VIT plus 1/2 AT squared. Now, this whole component is actually the A, just so you're aware. So take your acceleration in 1/2. All right, so we would use this particular quadratic formula to solve out for the t variable here. Because there's two of them, and because they are squared and a single, we would have to have both of them. So typically speaking, what you would do for this thing is you would take whatever value is x, which is xt at this point, you would push it over to this side algebraically, and have 0 equals, and then this new single value, which we're going to call c, plus the a value, which is b value, which is going to be the initial velocity, and then the a value, which is the combination of the acceleration cut in half. Okay. So we're never going to use this for you to solve this problem. Okay. So what we're going to do is we're going to use called the quadratic formula solver. It's just on our calculators, and it's a program that's just going to ask you for your A, ask you for your B, and ask you for your C, and then it's going to give you two values. Typically speaking, one is going to be real, and it's going to work out your problem, and then one of them is going to be sort of not working. Sometimes you get a negative time, and you can have a negative time. So, anyways, yeah. So that's what it looks like here. So, what would a quadratic look like? I mean, if we took, let's say, an object and you just pushed it, let's say a ball, and you roll it at a constant velocity, then the slope of a position time graph is going to look just with a constant. Remember, the slope for the position time graph is the velocity, so it might just look something like that. If I pushed it a little bit faster, okay, then maybe it looks like this. Okay. Well, when you're looking at your formula, xt equals xi plus vit plus 1/2 at squared. This guy, the velocity equals x, acceleration equals 0, and this guy, the velocity, let's say, equals 2x, the acceleration equals 0. Then at that point, when the acceleration equals 0, this problem becomes much simpler because this drops out. And I'm just going to be able to put in here my location initially and my location at the end, and then I can put my initial velocity and I can solve for time. And really all I'm doing here at that point is taking the time, and I'm just cutting up here and say at this time, okay, what is my current location? This is literally a linear situation. This is a y equals mx plus b situation. Nothing new here, okay? But what if we have an acceleration? Okay, that means my velocity is changing. So I can take, for example, and just the most common example might be just to throw a ball up, and it goes up, it slows to a stop, and then it comes back down. So now my velocity is not the same, and it's going to go up like this, let's say, and then it comes to a stop, and then it accelerates down the other way. And this is your parabolic path, and this is something that you would have now. Xt equals xi plus vit plus 1/2 at squared. And this is now, there is an initial position, could be 0, and then there's an ending position. Now, depending on where we solve for, my position here is different. And this is just the position here. So at the highest point, okay, then of course we know that this would be the max height. But either way, I have a t here, and now I have a t here. Okay, I have a component here, and I have these guys have components. If I were to use this guy in terms of gravity on Earth, it would be 1/2 times 9.8, okay, which is what, like 4.6. So at this point, some people get really common into just putting that in there right away, just so that, 4.9, sorry. So you can just take negative 4.9 right away and plug that in for this guy right here. So either way, okay, so that's an example what the graph looks like. And in all of our parabolic graphs, kind of our quadratic formulas, all are going to have this type of scenario. It could even be this way, okay? Could be this way. Either way, it's an arced curve. So next, all right, let's try. What would be some examples that we might use this for? So let's say our first one. A ball is dropped off a cliff, a 50-meter cliff. How much time for impact? So we have this cliff, and we're just going to drop a ball, and we're going to drop it 50 meters. Do I need the quadratic? Okay, so at this point, I have accelerating by gravity, so xt equals xi plus vit plus 1/2 at squared. Now keep in mind there are 3 different formulas that are the main tools we will use in this class, for the first part of this class. So the other one is velocity x, velocity final is what we would call it, or velocity at time t, I like that much better, squared, equals velocity initial squared plus 2a, and then it would be position xt minus x0 xi, so position final minus position initial. So either way, do I need to use the quadratic here? Well, first of all, so that's what I got here. Let's use this one here. Now, we set a frame of reference, so the initial position is 0. I'm going to call this 0. This would be negative 50 because it's going down. So negative 50 equals, all right, 0 would be that component, 0. Initial velocity actually is 0, so this drops out, or that guy is out. And then plus, I'm going to put negative 4.9 t squared. Do I need the quadratic here? No, do not need it. Okay, you should be able to use standard algebra to divide out the 4.9, and then we're going to square root this thing to get that equals my t value. Okay, could I use this formula? You could, but you don't know VF. Okay, you don't know the velocity at the bottom. I'm not saying you couldn't figure it out, but that you don't know the velocity at the bottom. Initial velocity is 0. Acceleration is negative 9.8. Final position is negative 50. Initial position would be 0. So I'm still missing 2. Well, this position just wouldn't give me the time. There's no time in here, first of all. Right? So there's nothing here that I can really use to solve for time. I could use it to solve for V f, final velocity. But I'm looking for time here, and I don't have any time in here. The other formula they give here is Vt equals Vi plus At. And again, there's time here, but we have acceleration. We don't have Vf. So I could use this particular formula to solve Vf, and then I could solve for that right there once I have final velocity, and then solve for the time in the air. So there's a couple different ways ways I can do things. All right, let's take a moment and look at the second problem. Okay, now the second problem says it's thrown down at a velocity. Now this is a little different scenario here. Okay, so I have xt equals xi plus vit plus 1/2 at squared. Xt is going to be my -50. I want to know how much time it takes to impact the ground. Remember, when it hits the ground, its velocity is not 0. Okay, it's after it hits the ground, but the math doesn't know it hit the ground. So it wants to know just prior to impact. 0 plus vi is going down, so a -2t plus 1/2, and then the 9.8, and then of course we want that to be negative t squared. All right, so at this point, how do I solve for t? So the quadratic would be a great option here, especially with quad solver on your calculator. Without a quad solver in your calculator, it's going to be much more laborious and maybe not something we would do in this class. But let's move the 50 over to 0 equals positive 50 minus 2t plus minus 4.9t squared, and now I have myself an A component, I have myself a B component, and I have myself a C component. So let's take a moment and let's just solve it out. Now again, if you have a quad solver, you can always pause in the video to try it out. But I pulled up a one online, and this is something that if you can do. Okay, so the A component is negative 4.9. Okay, the B component was -2. That's the velocity, and it's graphing this out for us very nicely here. And the ending one was 50. There it goes. So it's graphing. In case you can't tell, it's got a kind of a large loop here, and at that point, this guy is going back in time, so that's -3.33 is not really a valid answer. Graphically, it might work, but 2.9996. Okay, so essentially our answer here is about pretty darn close to 3 seconds. Okay, so the t equals about 3 seconds. Okay, and that's how long it took to get to the bottom. Did I absolutely have to solve it this way? I didn't. I don't. You know, I could use potentially, let's say, this formula right here. Combination of formulas. Okay. Let's take this guy for example, and let's solve it out without the quadratic formula. Okay. And let's try this guy. So I have velocity final squared equals velocity initial squared plus 2 times the acceleration of gravity, and then position final minus position initial, and let's use that guy. I'm going to solve for VF, and then I'm going to simply use the formula VT equals VI plus AT. Okay, and I'm going to plug this guy into here. Okay, all right. And let's do it. And these are the formulas that are available to you. You could just grab them and use them. So initial velocity is -2 plus 2 times -9.8. And then the initial final position is -50. Okay, and then -0 initial position. All right, and then this guy is going to get plugged into here, and we'll solve for the time. And then that works. Okay, so at this point, you know, I'll let you guys at this point figure this out. So solving for t would just be subtracting over. Let's do it quickly. All right, so let's do this first part right here. 2 times 9.8. Okay, now the 9.8 is negative, so 2 times negative 9.8 equals 19. Negative 19, so this guy is negative 19.6. Multiply times negative 50 equals 980. Okay, so this whole component here is 980, and I'm going to add the plus vi squared, plus that would be negative 2 squared, which of course becomes positive 2, and I get 967. So now I get velocity final squared equals 976. Now I'm going to square root both sides to get rid of that square component. I'm going to square root the previous answer and square root the previous answer, and I'm getting velocity final, VF, equaling 31.2 meters per second. All right, let me plug it in here. Okay, I'm going to re-solve this program for time. So VF minus VI divided by acceleration gives me time. All right, so VF is 31 minus a negative 2, and this would also be negative 31. And then acceleration is that of gravity, negative 9.8. All right, so negative 31 minus a negative 2 equals negative 29 divided by negative 9.8 gives us a positive value, and I got about 2.95 seconds. So do you have to use the quadratic equation? No. All right? No, you don't. So it's just an easy way to solve out for something. Okay? And we'll go for there for now. Thank you.